All right, welcome everybody. As you're coming in, I know they ran late. The keynote. If we got plenty of seats down front, come on down. I know it's an intimidating walk, but anyway, um, my name's Sandon Jacobs, and we're here to talk about Apache Kafka, specifically Apache Kafka as it pertains to point-to-point messaging. Any Kafka users in the house? Raise your hand. Kafka, like it, love it. Oh, there we go. When it works, right? Again, I'm Sandon Jacobs. I'm based out of North Carolina, Raleigh, North Carolina, in the U.S. I'm a developer advocate, a senior developer advocate at Confluent. How many of you have heard of Confluent before? Yeah, nice, nice. Love Confluent. Hey, there. Name a JVM language, and I've kind of kicked the tires on it. You know, Java, Kotlin, Clojure, except for all the parentheses and the Emacs stuff. You Emacs folks, I got nothing against you. In fact, much respect. But anyway, Scala even. Any Scala developers in the house? There we go. There's always one. There's always one. Here's what we're going to do today. We're going to start talking about, start off with event-driven architecture a little bit. We won't go too deep, but we will talk about event streaming and kind of comparing that to point-to-point messaging or your task and queue-based type of workflows. then we'll dive into queues for Kafka, what that means, what it is, how the API is constructed, and what happens on the broker side for that. And as time permits, we'll look at some code and a simple live example that I have. Okay, we good? Sounds like a plan. So event-driven architecture. Where did this event-driven microservice architecture come from? Well, after we broke up the monolith and we built small applications that talk to each other over synchronous protocols like HTTP or RPC, we realized we had just distributed the problems, right? So if there was a service that was central to our nervous system or was mission critical that went down in our beautiful microservice architecture that we created, then the stuff hit the fan. And by stuff, you all know what I mean by that. So we learned the lessons of, can we do this using event protocols like JMS to start with, or your MQ systems like ActiveMQ, IBM MQ. And the folks at LinkedIn went a step further. They said those things don't scale to what we need. So then they created Apache Kafka. And what Apache Kafka allowed them to do is the different parts of your LinkedIn ecosystem, that page that you load, it's all a lot of different apps. And those apps need to talk to one another when there are changes to be made, when there are things that come up in your feed. Other parts of the application need to know about it. And so Kafka was born to address that scale-driven need they had for messaging. So let's talk about this event streaming ecosystem specifically with Apache Kafka. We're going to start out by talking about the producer side, or the applications that actually write events to Apache Kafka. Those are called producer applications, and your producer creates a producer record or an event that looks something like this. It has three parts. First part is an optional set of headers. These are just key value pairs. Think of it as metadata about your event. It could be used for things like distributed tracing or routing, logging, things of that nature that you want to convey throughout the process of the event system, but they aren't really a part of the value of the application. It may be metadata about who wrote it, or metadata about related information to that event from the writing system. The next part of that is the key. Key is optional as well, but key plays a vital part in something we're going to talk about later, which is partitioning. And the key, as the name implies, is an identifying piece of information about that event. Think of key to a database table, right? It could be a simple type like a string, a long, an integer, but it could also be a complex type. You could put complex objects in here like JSON structures or Avro objects or protobuf. And the last part of that event is the value. And the value is really what I call, in American parlance, the meat and potatoes of the event. This is what we actually are talking about. This is what happened that we want to convey to the rest of our organization, the rest of our ecosystem. The example here, you see this is JSON, but typically this would be serialized as something like JSON or Avro or protobuf, like I was talking about before. It could be a simple type, but what is the richness in a message that just has a string in it, or just has an integer value or something in it? We really want to convey events that are occurring from applications that are producing them, and give context to our applications downstreams that are consuming them. So we talked about the key. and we talked about partitioning, and this is where that comes into play. When you're writing to Kafka, you're writing to a construct called a topic, and I call Kafka the durable, replicated, immutable. I think I already said durable log. Partition log. That was the other thing. So when you produce a message or an event to a Kafka topic, given that key and given the metadata about the target topic that you're writing to, something's going to happen there because the producer has what's called a partitioner assigned to it. And that partitioner takes that key, takes the metadata about the target topic, and says, to which partitions should I route this event? Events of the same key will always go to the same partition of that topic. And that comes into play later on on the consumption side, because that guarantees, because this log is immutable and because these messages are stored in the order that they're written, that on the consumer side, in your typical Kafka consumer, you're going to consume those events in the same order that they're written. That comes in handy when order is of the essence, because think of something like a bank balance, where you're looking at bank transactions or order transactions. It's pretty important that we get those debits and credits in the same order, in the right order that they were written, right? So inside of a topic partition, there are some attributes that you'll see other than just the event that we talked about with the headers, key, and value. Each event is assigned an offset. That is a position in the log where that message is stored, and it's relative to the messages in front of it or to the beginning of the log. That gets us to the consumption side of the house. And because we have this information in Kafka now, we start a consumer application. And if we start a consumer application, we have to configure it with certain properties, not just to connect to Kafka, but also in order for that consumer to participate in what's called consumer group coordination. Because we're building a group of consumers to hopefully consume from the topics in parallel, consume each partition in parallel. So we give that consumer a group ID property. And when we add more consumer instances with that same group ID property, they cooperate, or they participate in this activity known as consumer group coordination. And what that does is that manages the partition assignments of the targeted topics to members of the consumer group. But as you can see, if order is of the essence, then we can only have this ratio of 1-to-1 consumer to partitions of a topic. If we started another instance of our consumer that is beyond the count of our partitions, then that's going to be an idle consumer. It's not going to do anything until one of our other consumers drops out or the rebalancing process happens for that consumer group. And if we look at how traditional Kafka consumers are created, pre-Use for Kafka, here's how we do it. This is Java, of course, and here we have how to connect. We're creating a properties object that we're going to use to instantiate our Kafka consumer. It tells us how to connect to Kafka to get that metadata, our group ID assignment, and how often we commit the offsets of our process messages back to the broker. What do I mean by that? Well, what a Kafka consumer does is as it polls for events, it's going to periodically report back home or call home to say, I have processed message 1, message 2, message 3, or event number 1, event number 2, add that offset, such that anytime I shut down a consumer, or if this consumer group completely dies, if I start it up again, then those new consumers of that same group ID know where to begin in each partition of the log. It can start from that point in time and move forward. So now that we have our properties for our consumer group, we instantiate a new consumer, we tell it which topics to which we want to subscribe, and we poll for events. Here we're polling for 100 milliseconds to say, give me some records. And once we get those records, we process them. Simple enough, right? As I talked about before, the problem with this is that I can't scale beyond the number of partitions of my topic. I get parallel processing, yes, and I get ordering guarantees, but what about some situations where I just need more power? That's a Star Trek reference for those of you in the house. There are things I could do. I could just add more partitions to my topic, but what does that get me if I over-partition my topic? Well, one, it gets me a lot of network traffic on the back end because of the replication factor of my topics. If I say I want 6 copies of every partition across my cluster, and I say, here's 100 partitions of this topic. Well, now I've got a lot of network traffic, and we know that our cloud providers love it when we do something like that because they smell money, right? um, and also, we're over provisioning for this situation that is not our steady state. If our steady state is we can handle this with 3 to 6 partitions, why are we going to go to 100 just for that fire sale situation where maybe we're a retailer and we send out a notification to our customers and everybody rushes to the website to buy new shoes? That only happens maybe 3 times a year. Let's talk a little bit about point-to-point messaging, and we'll see how some of these task-driven or work queue-driven use cases work in our traditional messaging systems and how we can bring that into Apache Kafka. We have a task here in a queue that is just some piece of work that a producing application has said, I want this done. I don't necessarily care about it being done in order, but I just want to guarantee that it's done. Anybody ever heard the term fire and forget when it comes to messaging? That's where we get that from. A message, we want that message to only be consumed by one process. And we want message level acknowledgement, meaning we want to know when message 1 is done, message 3, message 5, when those are actually completed, when they have been processed. And from our explanation of how Kafka consumers have worked previously, you can tell that's not really a great fit for Kafka before KIP 932. It's sort of been that square peg in the round hole, right? Until now, with queues for Kafka, or KIP 932, as the author created it. What is this paradigm, and how do we get here? Well, the term queue is in the name. I know it's there, and we're going to say the word queue quite a bit. But think of this more as a cooperative consumption model, where now we're allowing multiple instances of consumers of the same group ID to work on the same exact partition. We want to get these message level acknowledgments, and how we do that, when we use the API, the Java API, to create these new consumer instances, on the broker side, it creates what's called a share partition. Now, that share partition is a mapping of the status of the messages in a topic partition for a specific group ID or share group ID. So now we can go beyond this one-to-one relationship of partition to consumer, and we can have multiple share consumers on the same partition. We'll talk about how we get there with the API, and then we'll go into more depth on the share partition in just a moment. But message level acknowledgement is really the key here. And the default mode in our API for message level acknowledgement is this implicit notion, where we just want to acknowledge every single message that we pull and process as being done. This is the pie in the sky, go right path, where there's no exceptions or any exceptions that we actually care about. We just want to try to process these events. So we don't set that share acknowledgement mode. It's implied. It's the default value. And you can see here the API looks a lot like the Kafka Consumer API that we've seen before, except for the class name has changed. Kafka Share Consumer versus Kafka Consumer. Now that new class is what triggers the behavior on the broker side. Again, we subscribe to a list of topics, and then we start consuming, or we start polling those topics for messages or for consumer records, and we attempt to process them using that do processing method that you see there in the while loop. But things go wrong, and engineers, we have to be control freaks for when those things go wrong, when those exceptions occur. And not all exceptions are created equally. And that's why there's another acknowledgement mode called explicit that we could set in our properties object that we pass whenever we create our Kafka share consumer. Now, if we do this, if we set the acknowledgement mode to explicit, that means that we, as the name implies, the developer, have to explicitly tell the consumer how to acknowledge each and every record that we poll for. So you see not much has changed other than the properties here. We get into the while loop, though, as we're polling for records. When we get those records back, we have now introduced a try-catch block to be able to handle any exceptions that happen during our do processing method. And If that due processing method is fine for that record, if it's successful, then we actually call a method on the consumer called acknowledge with that specific record and tell it that we want to accept this record as being processed. We pass it an acknowledgement type enum value. What about the cases where stuff goes sideways? Well, we have some granularity here. Right here, I'm just catching exception, but we could catch different types of exception and use different acknowledgement modes for each, or different acknowledgement types for each one of those exception types. In this case, I'm just saying for this record, I want to release it. And we're going to explain in a minute what those mean, accept and release. And then there's two other types called reject and renew. We'll get into those in a minute. But again, all exceptions aren't created equally. This behavior here when we call this acknowledge method drives a state machine on the broker side within the share partition as to what the acknowledgement at the message level really means. So let's dig into that. This is kind of what a share partition looks like on your broker. Full disclosure, the share partition is not a copy of the events, so you don't have another copy of the events on disk. What you have is a pointer to that topic partition for that share partition with some extra metadata about the event. You have the offset, of course. You have the event itself, but you also have a couple of other properties here that the share partition manages for you via this Kafka ShareConsumer class. One of those is a state. Those states are available, acquired, acknowledged, or archived. Available, as the name implies, are events that when we poll, they're available for us to pick up. Acquired are events that have been picked up by a poll of a consumer. And acknowledged and archived are terminal states. That's the end of the road for an event. Once it gets to one of those states, this group will not process it again. Okay? So let's see what happens in the go right path, the first path that we looked at with regards to acknowledgement. Excuse me. So when we grab an event, we poll for an event, we got event number 1 here, and you can see that event, the state changed from available to acquired. Also, what changed is this delivery count. The delivery count is a tracking number for the number of times that an event has transitioned from the available state to the acquired state. And what that sets up for us later on is sort of a retry mechanism here that I'm going to show you on the next slide. When we move to the acquired state, this starts what I call a lock and a clock. So moving this event from available to acquired means other members of my consumer group can't grab it. That's the lock. But it also starts a timer to say you've got 30 seconds by default to process this event or to acknowledge this event. Tell the broker what to do with it. Otherwise, the broker is going to take some automatic action on it. Say you polled for this event and then your JVM went down. Well, the broker needs to take some action. So you've got a finite amount of time to tell the broker what to do with the event. So now that we've transitioned to acquired, we want to say that this message was processed successfully. We use the acknowledgement type of accept. And then on the broker side, what happens is this event moves to the acknowledged state. As you can see, the state transition at the top. So you see these two pointers at the bottom, SPSO and SPEO. What do those mean? SPSO is the share partition start offset. That is the position of the first available or acquired event. That is the offset for it. You take that offset and you add 200 by default to it, and that's where the SPEO, the share partition end offset, will be located. And that window in between is called the in-flight records window, meaning that anytime a consumer polls, that's the window from which it will grab events. It won't grab them from outside or beyond that SPEO. It won't grab them from before that SPSO. It says, okay, we can start here and we're going to look within this window and pull X number of events that we've configured in our properties object that we use to instantiate our consumer. That's where we're going to grab events from, okay? That's great for the go right path. What about when things go sideways? All right, so we're going to grab message number 2 here. It's going to go to the acquired state. Its delivery count has been incremented, and something happened with this event, meaning that maybe it's a garbage event. Maybe it doesn't pass some validation in our processing. Maybe it's something we can't deserialize. In that case, we're just going to move on with our life here. We're going to archive that event. We're going to reject that event so that the share partition marks it as archived in a terminal state. And you see that the SPSO and the SPEO move. That in-flight records window advances to the next record. I talked a little bit about a retry loop and how delivery count plays into that. Here's a scenario where we're going to get event number 3, and we're going to increment its delivery count. And we encounter some error of some type. Maybe it's a processing error. Maybe it's some type of exception where we were connecting to an external system. It's an intermittent issue of some type. It's something worth retrying to us. In that case, we use that acknowledgment type of release. And what happens then on the broker side is the broker evaluates the delivery count of that event versus a configurable setting within the broker. In this case, the default for that is 5. It says, how many times have we tried to process this event? Well, we've only tried to process it once. 1 is less than 5. So we're going to transition that event back to the available state so that another member of our consumer group, our shared consumer group, can poll, grab that event, and try it again. So what happens when we exhaust our retries? Well, now we're at delivery count of 5. 5 is not less than 5. And what happens on the broker side is it archives that event and moves us forward. Sorry about the spacing. I was playing around with that at 12 o'clock last night. What about long-running tasks? What about things that go beyond that 30 seconds that we talked about? After all, think about point-to-point messaging differently than event streaming. Event streaming is really drinking from the fire hose, right? My introduction to Kafka was in the real-time bidding space, where we processed 150,000 requests per second, and we had all these events coming into Kafka, and there was a lot of filtering, a lot of matching, a lot of other logic that went on to narrow that data pipeline down to a set of events that we actually cared about. And then there were some task-driven or very non-order-based eventing that we wanted to do, processing that we wanted to do on that data. So this case is where we take that specific task or that specific event, and we want to fire off some task that may run longer than our 30 seconds. Doesn't mean that it's a failure. LLMs aren't instant, are they? Takes a little while for them to return. Maybe it's a partner integration that we're trying, and it's going to take a while to get our response back from it. 30 seconds is a long time in processing parlance. I know that, but the point here is that if you wanted to run a longer running process from your queue-based workloads, you could do that here. And what you would do is periodically just call renew so that the lock doesn't expire on that event on the broker side. And as you do that, you continue your processing, and eventually you acknowledge that event with the accepted type, and it goes to the acknowledged state. So at any point in time, this is what our share partition could look like. And I kind of jumped around with the numbers here to show you that the SPSO and SPEO, that difference there is 200 events. You can see here that ordering guarantee that we have with our typical Kafka consumer is kind of out the window, right? Because of message level acknowledgement. We have multiple consumers coming in, they're polling for events, and message 5 could get processed and acknowledged before message 2 does. These are use cases where order doesn't matter. We just want to get stuff done. I want to keep reiterating that with you because those of us that have been around the Kafka ecosystem for a long time, we're used to ordering guarantees by partition. Here's some of those broker configurations that I talked about. The delivery count limit. These configurations that I talked about in the state machine are at the broker level right now. Maybe at some point they could come to your actual consumer group instantiation where you could get a lot more granular. These are just defaults that we've tested with, our engineering teams have tested with quite a bit. And these allow multiple share groups to be good corporate citizens within your Kafka cluster. So there's the delivery count limit, which by default is 5. That's how many times it can a message can transition from available to acquired before we exhaust the retry loop. The lock duration in milliseconds, that's the 30 seconds I was talking about whenever we go from available to acquire, that's how long that acquisition lock lives on the broker side, unless we tell it differently. And then the in-flight records window is the max record locks. That is the distance between the SPSO and the SPEO that we talked about. Okay, you want to see it in action? See some code? I'm going to give you a sort of practical, real-world-ish example first of how this looks in a browser, or how this looks in a lifetime situation, something we can all relate to, and then we'll look at code that I wrote for a specific use case that shows you some of the parts of the API. How many of you have been to a restaurant and you thought your food was just slow getting out? Well, maybe the restaurant's packed. Maybe they've only got one chef working. There's other chefs that are doing other things. Steady state, though, that one chef can keep up with the typical load of the restaurant. But if we start generating more orders, we'll see that we need some help here in order to keep up, because if we look at our metrics here, we can see the queue depth is growing. Now, this is built on Kafka. It's backed by a topic that only has one partition, and we did that so that you can see that we can have multiple consumers of that one partition. And so you'll see here that the queue depth is going down, and as we are processing these events, excuse me, as we're actually getting done with the work, we're checking periodically to see the depth or how many pending records there are out there, and we're scaling down. Think about this in your Kubernetes environment. How many of you are running in a Kubernetes environment here? That's why you went there, right? So you could elastically scale. So I could say, hey, if I'm running behind, spin up some more pods, get this work done, and keep checking this metric using something like Keta, to where at some point I can scale back down, save some money. I only need to spend money in spurts where I actually have the load to justify it, right? So that's a practical example. I'm going to show you some code now that may or may not be related to that whatsoever. This is this is an app that I wrote. Doesn't have a sexy front end to it. That's why I didn't show it here. But you can see here how the APIs are very similar. I use the Kafka ShareConsumer within a try with Closable. Everybody see that? Is that good for everybody? And here I'm actually tracking the time I've spent on these events, so that I know whether or not I need to call renew if there's an issue, or if I'm running long, because I do have some randomization functionality in here that says, hey, every now and again just sleep, so that I have to trigger my renewals. There you can see I'm running some task, and if that task is successful, then I actually call acknowledge to accept it. I've got a bunch of logging in here because I'm paranoid and I like to see things in the logs every now and again. And if unsuccessful, if there's an exception, then I'm going to release this event. I'm going to take advantage of the retry mechanisms that are a part of the API. And otherwise, if I'm running along here, then I want to renew my lock because I'm still working on this event. That's basically the gist of it. So I'm going to go back here and land the plane with some more talk about Kafka Share Consumers. Here's where we are in the lifetime of this KIP 932. Back in September, it went into preview mode in Kafka 4.1. As of Kafka 4.2 in February, that release means that Queues for Kafka is production ready. We have some consumer lag metrics in there now. That was one of the final things we were waiting on, just to give people observability into this and how their consumer groups were behaving. I have a YouTube video, a Lightboard video that I created. If you go to Confluent Developer YouTube channel, you can see it there. It's an explainer where I get into details, a whole lot more detail than I did here, on the actual share partitions themselves. Sort of the broker inner workings rather than just the API. And where we're going next with Kafka 4.3 and later, one of the things that's being talked about in this release is dead letter queuing. You can see in the state machine when we went through there that we were just discarding some of these events because we couldn't process them. That's probably not the best behavior. We probably want to get some human eyeballs on that, or get another process to have a look at that. Um, from what I've seen in the KIPs, that's going to be a configuration that's available to you to where you can say, when I reject this event, route it to a DL queue, and we'll check on it later. Delayed retry or exponential backoff in that release loop when the delivery counts were less than the max. I don't want to necessarily retry that instantly. I don't want another consumer to come along and just start hitting whatever external system that was that caused the problem. Maybe we put some kind of timer interval in there. That's being discussed. Rack-aware partition assignments, just to make for the efficiency of share consumers talking to the cluster. I put key-based ordering in there because it got talked about before. I'm not sure if I should even keep this in the slide deck anymore, but I have been talking to a few engineers about it. Can we do key-based ordering with this message level acknowledgement? That would be quite the feat. I'm not sure how it would be done, but that's something to think about. So in conclusion, I just wanted to point out here how differently this cooperative consumer model is than our traditional Kafka consumer groups. Now you can scale beyond the number of topic partitions. You're not limited anymore. We're not limited with that specific API. The Kafka Consumer API is still there for you for your event streaming use cases. Good news is that data is all still in the topic partition. If you have multiple use cases, some that are event streaming and some that are point-to-point or task-driven for the same exact data, run both of them. It's fine to do that. This Kafka Share Consumer gives you this message level acknowledgement and a built-in retry mechanism. The other thing is your producer code didn't change whatsoever. Your producing applications still write events the same way they always have. Nobody's influenced on that side. You know how in ActiveMQ, and I remember this from my horror stories of WebSphere MQ back in the day, there's a max queue depth where your broker will start back pressuring the applications that write to it. You don't necessarily have that issue here with queues for Kafka because typically in Kafka, if you got disk, you're good. So if you're using open source Kafka or managing your own Kafka, just be sure you provision your data volumes appropriately. And again, as I mentioned, you can process that same exact data with stream processing or point-to-point. So here's some more resources on queues for Kafka. The author of that KIP is a man named Andrew Schofield, and ironically, he came from an IBM WebSphere MQ background, where he worked on MQ at IBM years ago. And so bringing that point-to-point messaging to Kafka was kind of second nature to him. He understood the concepts really well, and so he authored the KIP. And he has some really good resources out there about it. On Medium, I think is where that article came from. There's the QR code for it. There's the QR code to my Lightboard video, and also a piece I did in InfoWorld about this that links to some examples. So if you want to grab those, you can. That QR code will get you to all of that I just showed you. This is my link tree. All of my socials are there. The slides for this presentation will be on there by end of the day. They'll be in my speaker deck account. So if you're interested, go grab them from there. I'll add some more resources, links to the repo that had that restaurant demo as well. I'll put those out there for you. And thanks for coming. I know the keynote went long. I appreciate all of you coming in here and filing in and filling in the front rows. That was great. But thanks and have a great day. Enjoy the conference.